Lecture 91. Science of Survival in Extreme Conditions in the Blistering Heat of Death Valley, where temperatures soar to 134 degrees Fahrenheit. In the crushing depths of the Mariana Trench, where pressure exceeds 1,000 atmospheres. On the forbidding summit of Everest, where oxygen molecules grow scarce and elusive, we find humans, not just surviving, but pushing the boundaries of what our bodies and minds can endure. Standing at the precipice between life and oblivion, challenging the very limits nature has imposed. Welcome to the enigmatic realm of survival science, where the confluence of biology, technology, and psychology creates a fragile sanctuary in environments that seem designed to extinguish life itself. I'm Dr. Eleanor Reed, and today we enter the mysterious frontier of extreme survival. What compels us to venture where every breath becomes a conscious act of will? What secrets has evolution woven into our cellular architecture that allows us to adapt where adaptation seems impossible? And when our biological limits are reached, what ingenious technologies have we conceived to extend our presence into realms that would otherwise remain forever alien to human experience? These questions draw us into the captivating science of survival, a domain where the boundaries between possibility and impossibility blur into a hazy twilight. In the next 25 minutes, we'll explore three dimensions of this science: the physiological extremes our bodies can withstand, the technological innovations that expand these boundaries, and the psychological factors that often determine who lives and who perishes when faced with nature's most formidable challenges. The knowledge we uncover applies not just to adventurers and explorers, but contains profound insights for all of us navigating the smaller extremes of everyday existence. Let's begin with our most intimate technology, the human body itself. This remarkable biological machine operates within surprisingly narrow parameters, yet possesses astonishing adaptability when those parameters are breached. Our normal core body temperature hovers around 98.6 degrees Fahrenheit, with even small deviations causing serious impairment. Yet humans have survived internal temperatures as low as 56.7 degrees, as with Anna Bajenholm, a Swedish doctor who survived after being trapped under ice for 80 minutes. At the other extreme, Rhonda Liskey survived a core temperature of nearly 114 degrees Fahrenheit, a temperature at which proteins typically begin to denature. How is this possible? The answer lies in our body's extraordinary defense mechanisms. When confronted with extreme cold, we employ a multi-layered response. Blood vessels near the skin constrict to minimize heat loss, a process called vasoconstriction. Simultaneously, our metabolic rate increases up to 5 times normal levels, generating heat through shivering. Perhaps most fascinating is how the body sacrifices periphery to protect the core, allowing extremities to cool dramatically while maintaining vital organ temperature. In extreme cases, this can lead to frostbite but save your life. In hot environments, the opposite occurs. Blood vessels dilate, allowing heat to radiate from the body. Sweat glands activate, releasing up to 3 liters per hour, each drop carrying away heat through evaporation. Our bodies can maintain this cooling system in temperatures exceeding 120 degrees Fahrenheit, provided adequate hydration. These mechanisms represent millions of years of evolutionary fine-tuning, allowing humans to inhabit nearly every climate on Earth, a feat unmatched by almost any other mammal. Yet temperature is just one variable in the complex equation of survival. Consider altitude, where each step upward diminishes the air's oxygen content. At sea level, oxygen comprises about 21% of the air we breathe. At the summit of Everest, that percentage remains unchanged, but the air pressure drops to 1/3 of sea level, meaning each breath delivers only 1/3 of the oxygen molecules. The haunting reality is that the summit of Everest lies almost precisely at the boundary of human survival without supplemental oxygen. Above 26,000 feet, the ominously named death zone, the body begins consuming itself, unable to maintain basic functions as cells starve for oxygen. Yet remarkably, some humans can endure these conditions. Mountaineer Reinhold Messner not only summited Everest without supplemental oxygen, but described the experience with the enigmatic phrase, "I am nothing more than a single, narrow, gasping lung." How is this possible? The answer reveals the body's remarkable adaptation capabilities. When exposed to high altitude, our physiology undergoes a transformation known as acclimatization. Red blood cell production increases dramatically, sometimes by up to 50%, allowing each precious breath to carry more oxygen. The body also produces more capillaries, creating extra pathways for oxygen delivery. Additionally, a substance called 23-diphosphoglycerate increases, changing hemoglobin's structure to release oxygen more readily to tissues. Perhaps most fascinating is that populations who have lived at high altitudes for generations, like Tibetans and Andean highlanders, have developed genetic adaptations. Tibetans, for instance, maintain lower hemoglobin levels but compensate with dramatically increased nitric oxide production, enhancing blood flow efficiency. These adaptations represent human physiology pushed to its theoretical limits, a delicate balance between survival and cellular collapse. The ocean depths present an entirely different set of challenges. Every 33 feet of descent adds 1 atmosphere of pressure, equivalent to the entire weight of Earth's atmosphere pressing on your body. At 100 feet underwater, nitrogen begins dissolving into tissues at dangerous levels. At 300 feet, oxygen becomes toxic. Yet the current world record for free diving stands at an almost inconceivable 702 feet, achieved without any breathing equipment. How do humans withstand such conditions? The answer lies partly in a set of ancient reflexes we share with aquatic mammals, the mammalian diving response. When our faces contact cold water, heart rate automatically slows by up to 25%. Blood vessels constrict, diverting precious oxygen to the brain and heart. Most mysteriously, our spleens contract, releasing stored red blood cells and increasing oxygen capacity, a biological adaptation so precise it seems almost deliberate. Elite free divers can extend these natural mechanisms through training, developing the ability to function with blood oxygen saturation levels as low as 50%, conditions that would render most people unconscious. Beyond temperature, altitude, and pressure lies a fourth dimension of survival: time without essentials. The rule of threes provides a grim countdown: 3 minutes without air, 3 days without water, 3 weeks without food. Yet even these boundaries have been breached. In 2012, Stig Severinsen held his breath underwater for 22 minutes, nearly 8 times what should cause brain damage. Mauro Prosperi survived 9 days without water in the Sahara Desert by drinking his own urine and bat blood. And Angus Barbary fasted under medical supervision for 382 days, consuming only water, vitamins, and electrolytes. These cases illustrate not just the flexibility of human survival thresholds, but how individual variation and psychological factors create a spectrum of survival capability that defies simple quantification. Yet despite our remarkable adaptability, humans remain fragile compared to the extremes that exist in nature. Our ingenuity has compensated through technological innovation, extending our reach into environments that would otherwise remain forever beyond our biological capabilities. Consider the space suit, perhaps the most complete environmental protection system ever designed. This personal spacecraft must protect against temperatures ranging from -250 to +250 degrees Fahrenheit, radiation levels that would otherwise destroy cellular DNA, and the vacuum of space that would cause bodily fluids to boil at normal body temperature. The current EMU, extravehicular mobility unit, used on the International Space Station, contains 14 layers of material including mylar, neoprene, and Kevlar, each serving specific protective functions. Yet the wearer remains separated from instantaneous death by less than an inch of material, a sobering reminder of how hostile some environments remain to human life. Deep-sea exploration presents similar challenges, but with opposite demands. Where spacesuits protect against zero pressure, deep-sea equipment must withstand crushing forces. The bathyscaphe Trieste, which reached the Mariana Trench in 1960, endured pressures exceeding 16,000 pounds per square inch, equivalent to supporting the weight of 50 jumbo jets on an area the size of a postage stamp. Modern atmospheric diving suits like the exosuit represent the cutting edge of personal protection, allowing humans to operate at depths up to 1,000 feet while maintaining normal internal pressure. These remarkable devices must solve complex problems of joint mobility, carbon dioxide removal, and thermal regulation, creating a habitable microcosm within an inherently lethal environment. What's particularly intriguing is how these technologies often mimic biological solutions. The articulated joints of atmospheric diving suits, for instance, employ principles similar to exoskeletons found in nature. In polar environments, survival technology has evolved through centuries of trial and catastrophic error. The traditional Inuit parka represents one of the most sophisticated thermal management systems ever developed, using layers of different materials to create microenvironments that trap heat while allowing moisture to escape. Modern polar gear continues this layered approach, but incorporates advanced materials like aerogel, the lightest solid known, composed of 99.8% air. Originally developed for NASA to collect space dust, aerogel provides the highest insulation value of any material, allowing explorers to endure temperatures approaching -100 degrees Fahrenheit with minimal bulk. Perhaps most fascinating is how polar survival technology must balance the paradoxical problem of overheating, even in frigid conditions. Heavy exertion can cause sweating, which later freezes with potentially fatal consequences. Modern fabrics therefore prioritize moisture management alongside insulation, an engineering challenge still being refined. While technology can extend our biological limits, perhaps the most mysterious frontier of survival science lies in the human mind. Psychological factors often determine survival outcomes more definitively than physical capability or equipment. Consider the perplexing case of the two hikers phenomenon documented repeatedly in wilderness disasters. Two individuals with identical equipment, physical conditioning, and survival knowledge encounter the same extreme scenario. One survives while the other perishes. The difference? Mental resilience. Studies of survival psychology reveal several critical factors. The will to live represents a quantifiable variable with measurable physiological effects, including altered hormone profiles that enhance both physical performance and decision-making capability. Particularly fascinating is how the mind processes time during survival scenarios. Those who mentally divide challenges into manageable increments demonstrate higher survival rates than those who become overwhelmed by the totality of their situation. This bite-sized approach to adversity appears to maintain critical cognitive functions that would otherwise be impaired by stress hormones. The case of Aaron Ralston illustrates these principles with haunting clarity. Trapped in a remote canyon with his arm pinned by a boulder, Ralston survived for 5 days before amputating his own arm with a dull pocket knife. In interviews, he described employing several psychological strategies, including mentally dividing days into specific tasks, maintaining a problem-solving mindset, and perhaps most importantly, connecting to personal relationships that gave meaning to his survival. This last factor, the survival for whom question, appears repeatedly in studies of those who endure against overwhelming odds. Humans demonstrate remarkably enhanced resilience when survival serves a purpose beyond self-preservation. The Holocaust survivor Viktor Frankl captured this phenomenon in his observation that those who have a why to live can bear almost anyhow. Recent neurological research suggests this isn't merely philosophical. Having a purpose for survival actually alters brain chemistry, enhancing both physical endurance and cognitive function. Training can significantly enhance these psychological factors. Special forces units worldwide employ extreme conditioning, specifically designed to expand mental resilience rather than merely physical capability. The Navy SEALs' infamous Hell Week, where candidates endure 5 days with less than 4 hours of total sleep, aims not to teach specific skills, but to redefine candidates' understanding of their own limitations. As one instructor explains, "We're not interested in what you can do when you're fresh. We're interested in what you can do when you're beyond exhausted, freezing cold, and every fiber of your being is screaming to quit." This approach recognizes a profound truth. Humans typically operate at only 40% of our actual capacity. By intentionally creating extreme conditions in controlled environments, we can access deeper reserves of both physical and mental endurance, expanding our survival envelope in real-world scenarios. As we conclude our exploration of survival science, we confront a perplexing question. Why do humans continually push these boundaries? What drives us to venture into environments so hostile that survival becomes an engineering problem requiring our most sophisticated technology? Perhaps the answer lies not in the practical applications of survival science, though these are numerous, but in what these extremes reveal about human potential. Each time we extend the boundaries of where humans can go and what we can endure, we redefine our understanding of what it means to be human. The physiologist Griffith Pugh, whose research made the first ascent of Everest possible, observed, "The value of Everest lies in its hostility to human life," suggesting that it is precisely in confronting our limitations that we discover our capabilities. As you leave this lecture, consider, what are the extreme conditions in your own life? What boundaries do you perceive as absolute that might, with the right preparation and mindset, prove permeable? The science of survival teaches us that the line between impossible and possible is rarely fixed. It shifts with knowledge, technology, and perhaps most importantly, with our willingness to venture into the unknown realms that lie just beyond our comfort. For Unusual Science, I'm Dr. Eleanor Reed. Thank you for exploring these boundaries with me. Music swells and fades,